Today, we're diving into a protocol that chances are is directing your internet traffic right this second. It's called OSPF, and it's basically the internet's invisible highway system. So let's just start with a crazy question. What if the map that guides all your data across the internet was actually a carefully constructed lie? It sounds like something out of a spy movie, right? But believe it or not, a pretty fundamental vulnerability in the internet's design makes it way more possible than you'd think. You see, every single time you hit send on an email or load a web page, your data gets routed using a kind of GPS for the internet. The system is called OSPF, and its whole job is to create the fastest, most efficient map for your data to follow. But, as we're about to find out, there's a critical flaw baked right into its design. To really get how this map can be forged, we first have to understand how it's drawn in the first place. So let's get properly introduced to OSPF. OSPF stands for Open Shortest Path First. Now, it's what's known as a Link State protocol. And all that really means is that every router running it is constantly talking to its neighbors. They're sharing info about all the connections they know about and the cost of using them. And you can think of cost as just a measure of things like speed and reliability. By sharing all this info back and forth, every single router builds an identical, complete map of the whole NIP. The whole process is kind of like a three-step dance. First, routers send out a hello to find their immediate neighbors, just to see who's online. Second, they exchange their maps. These maps are called Link State Advertisements, or LSAs for short. And finally, each router on its own runs a famous algorithm to calculate the absolute lowest cost path to every other destination. This ensures everyone agrees on what the best routes are. Okay, that sounds great for a small network, but what happens when the network gets massive with thousands or even tens of thousands of routers? If every router had to know about every single other router, the whole system would just collapse under the weight of all that information. OSPF has a really clever solution for this. It divides the network into these manageable chunks called areas. The best analogy is thinking of a country being divided into states. Routers inside one area know everything about their local neighborhood, but they don't need to know all the tiny, intricate details of other areas. It's a brilliant design for scaling up. And of course, not all areas are created equal. Some, which we call standard areas, accept all the routing information you can throw at them, but others are more specialized. A stub area, for example, filters out a lot of external route information and just relies on a simple default route instead. A totally stubby area is even more strict. This filtering is absolutely key to reducing the workload on the routers and keeping the network running fast and efficiently. And at the very heart of this whole system is the big one, Area 0, also known as the backbone. It's the central hub that connects everything. If traffic wants to get from, say, Area 1 to Area 2, it has to pass through Area 0. This is a strict rule, and it's what stops data from getting trapped in endless loops. It's the superhighway that connects all the different states. So we've got this elegant, hierarchical system that has basically run the internet for decades. It seems rock solid, right? Well, now it's time to find the crack in the foundation. Now, OSPF was designed with some security in mind. Important updates are flooded everywhere, so it's hard for one bad router to hide information. A connection is only considered real if the routers on both ends of it agree that it exists. And most importantly, there's something called the Fightback Mechanism. And this fightback idea is absolutely crucial. If a router sees a fake update pretending to be from it, it's designed to immediately scream out to the rest of the network with a correction. This is supposed to be OSPF's main defense against anyone trying to forge routing information. But what if you could be really clever about it? What if you could craft a lie so perfectly that the victim doesn't even see it as a lie? What if your fake map looked just like a harmless echo of the real one? This right here is the absolute heart of the attack. An attacker waits for a router to send out a legitimate update. Then they instantly craft a disguised version. Now the key is that the headers, the sequence number, the checksum, the age, they're all identical to the real LSA. To a router, these headers are like a fingerprint. The only difference is hidden deep inside. The actual map data is malicious. So here's the trick. When the victim router gets this disguised LSA, it looks at that fingerprint in the header and basically thinks, oh, I just sent this out. This must be a copy. And it completely ignores it. The fightback mechanism never gets triggered. But, and this is the scary part, for any other router in the network that gets the attacker's fake LSA before the real one arrives, well, that fake one becomes the truth. It becomes a race, and the attacker only needs to win that race in some parts of the network. Once a router is poisoned with the fake map, it will then reject the real map when it finally shows up because it sees it as a duplicate. The attacker has successfully and persistently corrupted the internet's GPS. So, okay, an attacker can rewrite the map. What's the big deal? What can they actually do with this power? Turns out, a whole lot. First up, link overload. They can redraw the map to funnel a massive amount of traffic through one tiny little link that was never designed to handle it. You get instant gridlock. It's a perfect denial of service attack. Second, and this is the really scary one, eavesdropping. They can reroute traffic that's supposed to be going to your bank, for instance, and make it take a little detour right through a router that they control. Now they can intercept and read all of that sensitive data. Third, they can just cause chaos with delivery failures. An attacker can create digital black holes in the network, basically convincing routers that certain destinations are totally disconnected. Any traffic sent that way just disappears. And finally, routing loops. They can actually trap data packets in an endless loop between two routers, consuming network resources until the packets eventually just time out and get dropped. It's pure digital sabotage. This vulnerability reveals a lot more than just a technical curiosity. It exposes a really fundamental assumption about the internet's architecture, and it forces us to ask a much bigger question about the systems we rely on every single day. The Stanford researchers who discovered this attack put it perfectly. For years, the common wisdom in the networking world was that this kind of persistent forgery was impossible. The system's own defenses were supposed to prevent it. But that wisdom, it turns out, was based on a flawed assumption. And that really leads us to our final thought. OSPF was built with an inherent level of trust, a trust that a router wouldn't be fooled by its own reflection. This attack exploits that trust completely. And it makes you wonder, how many other parts of our vast digital world are built on similar unspoken assumptions, just waiting to be challenged?